Hello, in this video we'll take an overview of section 5.3, double integrals in polar coordinates. Now you might think, why would we want to do double integrals in polar coordinates? Well, it turns out that it would actually be useful, not that we're going to be integrating over a bunch of those weird shapes that we saw like cardioids and limaçons and things like that, but rather because we could be dealing with circles. And circles would be a perfect time to use polar coordinates. So the regions that we're going to be looking at are essentially pieces of circles, whole circle, portions of circles, and if we happen to run into these more complicated looking ones, then polar coordinates would definitely be the big deal. Another strange shape that comes up quite a bit is this thing called the annulus, or we might remember it as the washer. From the integration techniques where we have volumes of revolution. So if these are your regions that you're going to be dealing with, then it is most ideal to be using polar coordinates, because then you're restricting yourselves. Instead of trying to find these graphs in terms of the Cartesian coordinates x and y, we're going to simply direct them to polar coordinates, and especially for these things that end up being circles, we're going to have constant limits, and that's one of the things that we're kind of striving for, are constant limits with these double integrals. And the idea there is that we're going to change our Cartesian graph into the polar coordinate graph. As we transform into these polar coordinate graphs, recall our transformation, x squared plus y squared is equal to r squared, and then r cosine theta for x and r sine theta for y. Now what we have to do is something significant happens when we change these variables from x, y to r theta. And what happens there, aside from the nice result where you're going to have constant limits in polar coordinates, we have to do some sort of transformation, because your area is not just going to be the x and y element, x times y element that we have, or the delta x delta y, but instead your area transforms into r and theta. And so within all this transformation, what's going to happen is that we're going to have an extra r that's going to come up. So this is I think the vitally important lesson in this section, is that when you do the transformation to polar coordinates and you switch your double integral, instead of dx dy or dy dx, when you switch that to dr d theta, you always have to have an extra r that comes out. And you can think about that as when you do a u substitution, or when you do a trig substitution, your dx becomes d theta with something else, or your dx becomes du with something else. And so that's the general idea here, is that we're going to come up with an extra factor to compensate for the way we changed from rectangular coordinates to polar coordinates. Okay, so after that, when we set up our integral, you change your dA or your dx dy or dy dx. Short, we call it dA. You change your dA to the r dr d theta. Okay. That is our quick introduction overview of section 5.3. Good luck.